My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So good evening to all here in Bangladesh and a very good afternoon to all those who are watching this program live from Poland. So hope we are well and safe from corona pandemic. So we know that we are staying in a corona pandemic situation, so we cannot continue our normal academic program inside the campus. We have to start our online program. I think you have already come to know that our Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. We have successfully completed our 115th international physics webinar. Today, it's our 116th international physics webinar. So we are trying to adjust with this new normal situation. So today, I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Cosmic Ray Research and Neutrino Studies, Institute of Nuclear Physics, Polish Academy of Science, Poland in physics. We have with us here today Dr. Gopal Bhatta, Professor, Department of Cosmic Ray Research and Neutrino Studies, Institute of Nuclear Physics, Poland, and he has already connected with us. So I'd like to welcome our speaker. So good afternoon and good evening here, sir. Welcome to our International Physics webinar, sir. Thanks for accepting our invitation.
Okay. So first of all, thank you very much for the invitation. I'm very happy to share my research to the students in Pabna, Bangladesh.
Thank you, sir. Thanks, sir. It's also a good opportunity for our students to learn a lot of things. So before going to start with you, so I'd like to introduce you with our student. So I think you have already come to know about our today's International Physics webinar, and the title is The Enigma of Multi-Frequency, Multi-Timescale Variability of Blazars. And our speaker is Dr. Gopal Bhatta, Professor, Department of Cosmic Ray Research and Neutrino Studies, Institute of Nuclear Physics, Polish Academy of Science, Poland. And we can see his educational career. So he has completed his bachelor degree from Tribhuvan University, Kathmandu, and master from the same university, and PhD from the Department of Astronomy, Florida International University. And this is his professional career. And we can see his area of research interest: multi-frequency variability study of blazars, supermassive black hole, galactic nuclei, quasi-periodic oscillation in blazar and binary supermassive black holes, particle acceleration and energy dissipation in relativistic outflows, very high energy, cosmic ray and neutrinos. And you can see his honors and awards from different institutions. So this is selected publications, and this is Google Scholar ID, and you can see citation is about 429, and this is his ResearchGate IT is 23.1. So thanks for all of your patience. Now it's time to go to our speaker. So thanks again for accepting our invitation. It's your time, sir. You can start your session.
Okay. Thank you. Thank you for the introduction. So I think I'm going to start my presentation today. So I would like, if there are students joining, and if you have any question, you can stop me or post a question through Facebook or anything. I'd be very happy to answer these questions. So the title of my talk is Enigma of Multi-Scale, Multi-Timescale, Multi-Frequency Variability in Blazars. I will introduce my material as we go by. So this is the outline of my talk today. So first of all, I will talk about what is active galactic nuclei, and then blazar jets, and their variability properties in different time scales and in different frequencies, for example, radio, optical, X-ray, gamma ray. And I will also talk about something called quasi-periodic oscillations in them. That's what you get to see, and their possible interpretations in the summary. So my main research area focuses into the multi-frequency observations of blazars. Blazars are kind of active galactic nuclei, and active galactic nuclei are kind of supermassive black hole systems. They emit the output in all the frequencies, including radio and X-ray and gamma ray. So we use space-based and ground-based telescopes to monitor, to record their flux modulations over a period of time, and try to study their variability properties. And let me introduce this active galactic nuclei. Many of you might have already heard about them. Active galactic nuclei is a special kind of galaxy, actually, galactic core. That core could be 1 to 10% of central region of galaxies, and these galaxies can be up to very far away, up to 6.4. This is kind of older number. The new number is, I think, somewhere 7 plus redshift, very far away and very early universe. And these are very bright galaxies, and they can be bright 10,000 times brighter than the usual galaxies. Only the core of the galaxy can be 10,000 times more luminous than the whole entire Milky Way galaxies. And so when you track them over the time and then record their flux in different frequencies, you find that their flux variations, their brightness changes over time very drastically, even in short time scales. And they are characterized by something called non-thermal emission as opposed to thermal emission of blackbody radiations. And then you can see them, the broad emission lines. And if you look at their spectra, you see a broad emission line, which are the signatures of something, some gas going very fast around some central source. And this is an indication of the supermassive black holes supermassive black holes lying at the center. These AGNs, the active galactic nuclei, are believed to host the supermassive black holes, which are billions times heavier or massive than our own sun. So billions times our masses. And they're surrounded by accretion disk, which can be from 0.1 to 1 parsecs away. So this is this accretion disk which fits the black hole with tremendous amount of material, so that it keeps on shining, and it keeps on eating the material and keeps on shining. And from the central the central region, relativistic jets can be seen. So these jets extended over kiloparsecs of the distance into intergalactic medium. So these are very interesting, very violent phenomenon observed in this kind of galaxies. These AGNs can be classified mainly into, there's a classification scheme, and the more widely accepted model is something called unified AGN model, which is based on the jet angle and with respect to the line of sight. The idea is that because most of the times they have the jet, so depending upon where this jet faces, its morphology will change. For example, if it faces right towards us, the relativistic or beaming effects will take over, so that it will appear very bright. So this is a unified AGN model. So in this figure, you can see roughly the AGNs can be of two types. One is radio loud, the upper part. In the lower part can be radio quiet. In radio quiet, if you look at the AGN face on, directly face on, then it looks brighter, and this kind of galaxies or AGNs can be called Seyfert-1 galaxies. But if you look them through an angle, a small angle, then they might not be as luminous as the Seyfert ones, and slightly less powerful. Than these are called Seyfert 2 kind of galaxies. So these are radio quiet, and although they emit radio emission, but in comparison to the radio loud AGNs, they are nowhere. Their radio emission is very weak. Therefore, they are usually known as radio quiet. But on the other hand, radio loud are distinctly distinguished by their presence of the jet, which is the immense source of radio emission. So again, this radio loud that has a jet with it can be classified into roughly into two kinds. One is flattest spectrum radio, FR1, something called Fanarov-Riley type 1 and Fanarov-Riley type 2. The classification is based on the fact that if you go away from the, if you start from central engine and go along the jet, if the radio intensity decreases, then it's radio loud, FR1 type. But if the radio intensity keeps on increasing as you move away from the central engine, then it's kind of Fanarov-Riley type 2. And the kind of sources we mainly study is blazar, in which case the jet faces the jet is directed towards the Earth, or a very small angle. Oops. Sorry. So these jets. So these are the blazar kind of sources, which has a jet which nearly faces toward the Earth, and they again can be classified into two subgroups, something called BLRs and flattest spectrum radio quasars. This classification is dependent upon you can see a emission line, strong emissions line, or not. So that's what blazars are. Now again, as I mentioned, these AGNs have jets which can extend up to kiloparsec distances. So these are the images in radio. This is the radio image and Cygnus A. You can see that this is central region is somewhere here, and then these are the jets extending parsecs away, and this is the hot spots and termination shocks here. This is Cygnus A, and then this is M87, the one which is the one you saw black hole picture last year. So this is the same galaxy, and in optical, this is an optical image. So you can see a jet coming from the system. So that's M87, and this is another AGN called 3C31. And see the jets are twisted, so which are possibly the indication that the galaxy is probably moving fast through a thick intergalactic medium, so that it appears twisted. So these are the examples of the AGN jets. And if this again, what are the blazars? Because blazars are the sources we usually study here. What are the blazars is if this jet points out at a small angle towards us, then the relativistic effects become very strong, and something called Doppler factor increases with this angle, and these sources appear very large, and any small scale fluctuations will be amplified and looks highly variable. So this kind of sources are called AGNs. Blazars, I'm sorry. The AGNs which have jets, which is nearly facing towards Earth, are blazars. So as I mentioned, the blazars vary in different time scales. It can be long-term, short-term, macro, or very short time, something called micro-variability, which can be in minutes to a day, very small time scales. And short-term, there are certain outbursts, flares, they often show, and this can last from few weeks to the months. And then there's a long-term variability, which can be 5 magnitude, meaning nearly 10 times. The brightness changes by 10 times or more, and this can last up to years and decades. And this happens because of the many different reasons, and it can be from change of accretion rates or the patches of shock waves along the jets or the turbulent jets. There are different regions. So these are the main topic of our study. For example, here I show you macro variability. It is in few hours. So what you see in this, there are two sources in this plot. One, for example, this one, a nearby star, so which doesn't change its brightness over this time. This time is few hours. And on the other hand, if you compare, this is the blazar. This is blazar 0716, and you see that in a given small time, its brightness changes so drastically. So these are the other different times, same source but different times. You see the variability in few hours. It changes and is drastically. Very interesting results. And back in 2014, what we did was, because these are optical observations actually. So if you you have to study about this small scale variabilities. You have to look through the telescope throughout the night. But the thing is that because of the length of the night, you cannot monitor them for more than 6-7 hours, because after that it will be daylight, so you cannot study the source during the day. So what we planned is we organized several, actually many, 17, more than 40 astronomers all over the world, including India, China, USA, and Japan, or many countries, and organized and we tracked one single sources for 5 days non-stop. And this is the light curve. So in what you see here is in time axis, you see time, and this x-axis, this is in hours. So the observation is more than 100 hours, and then the y-axis is a flux, which is indicating of its brightness. So you see that over that period of time, how the flux changes over this period of time. And this is 5 days nearly continuous monitoring of a single source. And from this study, we found that the question we ask is, what is the nature of this variability? What kind of? And for this, we study something called power spectral density. And this is this is called Lom's-Cargill periodogram. And in your x-axis is the temporal frequency, or the period, or the time scale. And the y-axis is the variability amplitude, something called power, which is indicative of the variability amplitude. So in this plot, you see that as the time scale increases, so the variability power gets stronger and stronger over time. What that means is that the source, in few hours, the source shows small amplitude variations, but over a period of long time, it will see a larger amplitude of the variation. That's the meaning of this kind of power spectral density, which are very important to explore into the nature of this kind of variability studies. And we also studied using polarization observation. So polarization tells, because earlier I mentioned that the emission mechanism is mainly non-thermal, meaning these are not blackbody radiations. These are the emission happens because the very energetic electrons or particles or protons plunge into the large scale magnetic field. And this is you might have heard about cyclotron emission. And if the particles are relativistic speeds traveling into magnetic field, then they emit synchrotron emission. And this is called non-thermal emission. And to explore this kind of non-thermal emission in optical telescope is to look at its polarization. And polarization tells how much polarized the emission is, and what is the tentative angle of orientation of this magnetic field. So these are very important kind of informations you get for this kind of observations. And what we found in this is, so we were looking into, is there any correlation between the optical emission and the polarized emission? And it's simple like that. This was studied something called cross-correlation coefficient, discrete cross-correlation coefficient. And in this case, what we did was we studied this cross-correlation as a function of the lag, meaning which comes first. It's possible that the polarized emission and the emission itself can come at the same time, or there could be some lead or lag between them. So in one case, we actually found out there's a 2 hours lead by the emission, and then the flux gets later after 2 hours later, and that actually tells about what's going on in these emission regions. These are indications of the magnetic field, and this kind of parameters. Similarly, in another observations, we found that they came actually both come, the flux and the polarization flux. They come at the same time. So it is not consistent. As you can see, that things might change in different ways. So that's very rich information that we get from this kind of. So that was about the optical observations that we did. And this is the space telescope observations. Something called the telescope is called NuSTAR, which actually observed the universe in something called hard X-ray band from 3 keV to 79 keV. So this is the observations of one particular blazar called 3C279. That's the name is, and this is a few hours. Again, the time is in kilosecond, meaning in few hours. This observation is. So as you can see, this is X-ray counts, X-ray photon counts in the y-axis. As you can see that within few hours, the sources changes its counts, and this is, so you see the spectacular variability patterns, and we also look into at the spectrum, the spectra, what kind of spectra it has. So this is the axis is the energy is equivalent to frequency. In X-ray, the frequency is more of it's a tradition to measure in terms of energy, and then keV, and this is the spectra. So it looks like the pure power law kind of spectra. This is the indication of the distribution of the high energy particle, how the high energy particles in the magnetic field are distributed. So it looks like there's a power law, meaning that there are more low energy particles and then kind of less very high energy particles in the magnetic field, and that gives rise to this kind of spectra. And so this was X-ray observations, as I mentioned to you earlier, and let me mention again that we studied these sources using various space-based and ground-based telescopes. And so when, as I showed you, some of the observations from optical and X-ray, and now this is the gamma ray observations. These observations were taken from Fermilab telescope, which looks into 100 MeV to 300,000 MeV, 3 GeV actually, in that spectral band. We studied 20 of blazars using the gamma ray observations in blazars, and as you can see that this is the observations of nearly 10 years, and you see several blazars. Look at the brightness changes, how brightness changes over time. It's very interesting observations over the period of time. And we explored the flux distribution, something called how the flux distributes. This can help you understand where does the variability come from, what source these are come from. So it looks like that the flux distribution is more can be characterized by something called log normal distributions, meaning that there are a large number of fluxes are from the lower energy, but then there are few are very high energy. So it's an indication of that there are probably two kind of populations of the particles which produce this kind of emissions. One very high energy, and the other is kind of average energy. These are the kind of informations we get. So again, I showed you the power spectrum, something called power spectrum earlier in the optical field, optical telescope, through telescope. This is the gamma ray power spectrum of one of the sources called 4C plus 38.41. So as you can see that this is a single power law. What that tells is that, so as the time scale increases, the variability amplitude is also increases over time. Now in this case, this is something called so what we do is we try to see the spectral slope in this log plane, and the spectral slope can be anything from 1 to 2 or 0.5 to slightly smaller than 1. So, but when the spectral index is 1, that's very interesting. That becomes very interesting. What that means is this is indication of long memory processes, meaning the very short time scale fluctuations somehow communicate with the fluctuations happening in large time scales, over long time scales, and they coordinate and maintain a single slope. And there's a very interesting kind of phenomenon, something called flicker noise or long memory. So the memory is encoded somewhere in the smaller regions and propagate into a larger emission regions. That's very interesting kind of observations. And also we study something called RMS flux relations. Here the question that you ask is that the source is there any difference between their fluctuations in higher state, or is there any difference when the source is very bright and source is not so bright? What are their variability patterns? So it appears that at the variability, the brightness becomes very bright. The variability also amplitude also increases. That's the meaning of linear RMS flux relation. And then there are on top of this kind of variability patterns, we look, is there any other kind of patterns we can see that? And this is called something called quasi-periodic oscillations. Do we see any periods in the light curves? And these are very important studies, because that might tell you something about the presence of binary black hole systems. Remember, if there are not one supermassive black hole but two supermassive black holes going one around, then they will produce the periodic oscillations in the light curves. And this is the subject of our interest, to look for this kind of signatures. And the first example of such periodic oscillation is something called OG87. So this blazars have been studied more than a century, and it has been found that every 12 years there's a flare in the light curve. As you can see, that is ABCD. So this happened more or less very regularly at 12 years. So this is actually the indications of possibly black hole, presence of supermassive black holes in this kind of AGNs. And this observation is PG 1553 plus 113 is a gamma ray observations. You see these nice oscillations with a period of about 2 years. So these are indications. There could be indications of the supermassive black holes. And let me just skip this method. There's another source, the OG7 that we studied, actually our group studies, and you see these fluctuations happening every kind of 400 days. And then, so how we know that? We looked at the power spectrum, and we see two significant peaks, and something called, we studied wavelet, and you see the strong signal at that 400 days time. So this is one of the ways to look at the periodic oscillations. Similar studies, and in this time this is another blazar, but in radio frequency, and we found 270-day quasi-periodic oscillations in this source. This is another source in which we see 560-day radio quasi-periodic oscillations, and we figure out using something called discrete correlation coefficient and Ebert folding. And these are the methods we see usually in time series methods. And moreover, we also found that such periodic oscillations are also present in gamma ray light curves. So as you can see, that this is the 5 blazars in which we we found actually there are some periodic oscillations, and these are very important. They still tell about this supermassive black hole and their vicinity, the strong gravity. The black holes are believed to be rotating very fast, meaning curved black hole, and curved black holes, they drag this space and time with it. So these emissions could be somewhere coming from those kind of extreme gravity environment, and these are very important. And besides, there could be other interpretations of this kind of oscillations. It's possible that there's something in the accretion disk which is rotating very fast and then producing this kind of periodic light curve. It's possible that, as I mentioned, the sources has jets, which is pointing towards us, and there could be jet precessing, and which can happen due to something called lens threading precession, in which the inner part of the accretion disk is precesses due to the strong gravity, due to supermassive black holes. Besides, there could be something in the disk, which is the magnetic field could be playing a role in producing this kind of signatures. So in future we will study this kind of models to look into what could be the possible to ways to explore in this kind of periodic oscillations. So one of the models, as I told you, is that there's one supermassive black hole with the accretion disk and this primary black hole, and there's another black hole secondary, and which punches into the accretion disk of the primary and produces this large sphere that you can see. This is one of the interpretation of this kind of periodic oscillations. Therefore, the other interpretation may be the beaming angle can be changed, because the brightness really changes depending upon what angle you're looking at. So if the jets or the emission region changes slightly angle, then you can see this kind of variations. So this could be another interpretation. So as I mentioned to you, there could be the jet could be precesses. If the jet precesses this way, and then it changes the angle of line of sight, and because of that, this kind of things might happen. And talked about the lens threading effect. So what happens that the inner region kind of precesses. This is the disk, cross section of the accretion disk. The inner disk behaves slightly different than the outer disk, and which can produce this kind of things. So moreover, there are studies doing the large scale jet simulations from the supermassive black holes, and these are also seem to produce such kind of oscillations. And this is the jet simulations done by these authors, and what they found is actually when they did the simulations and they did the power spectrum analysis, they found some of the prominent peaks around some time scales, and this can be the result of this kind of magnetic processes happening in the jet. So besides, there could be something moving on a helical magnetic field, because this the jet, and there's a magnetic field, and in some cases the magnetic field could be of helical shape. So if something is moving along this helical shape, then this can also appear as a periodic motions. And I think that's exceeded my time by 4 minutes. So I think this is finally my summary. So blazars exhibit very remarkable multi-frequency variabilities, which can be characterized by single power spectrum. And then in several of the sources, we see multi-frequency QPO, quasi-periodic oscillations. That can be a signature of binary supermassive black holes and a very interesting flux. And these blazars are the sources of very high energy emissions, and a very, very interesting source. So I think I'll stop here. And if there's any questions, I'll try to answer them. Thank you.
Thank you, sir, for your nice presentation, sir. We have got questions, so if you allow, we can start our discussion session, sir. And the first question: what is the basic difference between blazars and AGN and jets from spinning black hole.
Okay, so I think I introduced this thing a little bit earlier. So AGN is a special type of galaxy, whose core is very bright. It's so bright that it outshines the whole galaxy. So it has a very shiny core. That's so in that sense it's active in the sense that it is eating the material from the accretion disk, or the accretion disk is feeding the material into it, and the gravitational potential energy is quickly gets converted into emission. So that's active, and this kind of active galaxies may have jets or may not have jets, or very weak jets. If they have jets, then they're called radial out, and they have jets. And if they don't have jets or very weak jets, then they're called radio quiets. And if that jet, it happens that that jet points to turn towards the us, and then because it's the jet material is coming out of from the source with relativistic speeds, and then when it points towards us, then it will be appear very bright. And this kind of AGN with jets whose jet points towards us is blazar. So blazar is a subclass of AGN. And I think the other part was I'm sorry, could you what was the second part of the
So
question?
the jets from spinning black hole.
Okay. Uh,
So the
so it is believed that uh, the studies are going on, but it looks like that as you might know, a black hole. There's something called no hair black hole no hair theorem. So black hole, in some sense, black holes are very simplest kind of objects because they have only mass and angular momentum, something called spin, and a little bit of charges. So nothing else. That's it. Um, so in this case, it is believed that we usually do not talk about charge, which may not be important in this kind of studies with very small charge. So what we talk about is that they're very massive. As I told you, they're a billion times the massive than the sun, and then they have this belief that they have a very large spin, meaning that they're very rotating uh, black holes. And this is actually the could be the source of what drives these jets. The jets derive the powers or the energy from these fast spinning jets. Uh, so this is the one of the widely accepted model in which the spinning black hole is actually responsible for production of the jets in AGNs or blazar.
Okay, so thank you. So we have another question. So what is the mechanism of such high energy jets from spinning black hole?
This is something called blind for genetic process. So what happens that um, um, in car black hole, the you know the in sorcerer the uh, ISCO, the innermost regions of the orbit is closer to the black hole, very close to. In Schwarzschild is a kind of black hole in which it's non-spinning, spherically symmetric, so it has a Schwarzschild radius, right? And the any ISCO is meaning the uh, stable orbit of the innermost region is about 6 RG, meaning 3 Schwarzschild radiation. But in curved black hole, it can go very close to the black hole. So because of that, what happens that the spinning, remember in this spinning case, the spinning black hole drags the space-time with itself. And if there's a magnetic field, in the innermost curved black hole spinning fastest black hole, then this magnetic field can twist and kind of produce a dynamo effect. And because of this, and it can produce a very high electric volt, and which can accelerate these particles to the very large speeds. So that is the widely accepted mechanism for the launch of the jets from these spinning black holes.
Thank you, sir. We have another question. This may be the last question. So, are blazars the brightest things in the universe?
Yes, I think, yeah. The blazars are the most luminous sources in the universe. Yes.
So, thank you, sir. As we don't have any more questions, so we should conclude our discussion, sir. So, thanks again for accepting our invitation, sir.
Sure.
So, I think students have learned a lot of things about this field. So, and thanks for choosing my university for your webinar. So thanks again, and hopefully in near future we'll collaborate in research in this field.
Yeah.
So thanks for those also that you have agreed to be a collaborator of me and my student. So hopefully in near future we'll arrange another webinar with you, and I think we can start astrophysics in my university with help of you. So thanks again. And on the behalf of the Department of Physics, Pabna, University of Science and Technology, I'd like to say thanks again. So bye for today.
Okay.
And hopefully we'll meet very soon.
Sure.
Good night.
Yes, I once again thank you for the invitation. Bye.
Yeah,